This video accompanies Learning IoT with Python and Raspberry Pi. In this video, you will learn how to use Lambda expressions. Recall that a function that has parameters is defined using the define keyword, followed by the name of the function, and followed by a parentheses enclosed, comma-separated list of parameters. This line is a clause header of the function, and the suite is indented 4 spaces with respect to the header. The suite in this function is composed of a single return statement that returns the result of some expression. Suppose you wish to define a function that calculates the hypotenuse of a triangle with the 2 sides of the triangle passed as arguments. Let's name the function hip with a and b as the 2 parameters which represent the 2 sides of the right triangle. This function returns the result of the expression square root of a squared plus b squared. The hip function can then be called by passing 2 numbers, say for instance 29 and 25.7, as the arguments. A lambda expression can be created that behaves like a function. The syntax of a lambda expression consists of the lambda keyword, followed by a comma-separated list of parameters, followed by a colon, and followed by the expression to be evaluated. A lambda expression can be used to create a function object that evaluates and returns, for example, the hypotenuse. That is, hip is assigned the lambda expression, which is composed of the lambda keyword, followed by a comma b, which are the 2 parameters, followed by a colon, and followed by the expression square root of a squared plus b squared. The function can be used in the usual way. In order to calculate the hypotenuse of a right triangle with sides 29 and 25.7, you would pass these values to the hip function object. A lambda expression allows a programmer to create an anonymous function. The use of an anonymous function can be used to write shorter, neater code. For the first example, we'll write a script that calculates the position and velocity of a boat of mass 250 kilograms that initially has velocity 10 meters per second and experiences friction characterized by a friction coefficient of value 2 kilograms per second. We assume the boat's engine has been turned off at time 0. The position x is then given by the mass times the initial velocity divided by the friction coefficient times 1 minus e to the minus friction coefficient times time divided by the mass. The velocity v is given by the initial velocity times e to the minus friction coefficient times time divided by the mass. We'll write a lambda expression for each of these mathematical expressions. Since the exponential function appears in both the position and velocity expressions, we need to import it from the math module. Values are assigned to the variables representing the initial velocity, the friction coefficient, and the mass. Both lambda expressions are defined to have t as a parameter. The first lambda expression returns a function object that evaluates the expression m times v naught divided by b times 1 minus the exponential of minus b times t divided by m. The second lambda expression returns a function object that evaluates the expression v naught times the exponential of minus b times t divided by m. Finally, the position and velocity are calculated at 10 seconds, and their values are printed out. Let's run the code. We'll next consider a script that illustrates how using lambda expressions can make code neater. We'll consider the same boat problem that has initial velocity 10 meters per second, friction coefficient 2 kilograms per second if the boat is to experience friction, and mass 250 kilograms. The user will have the option of choosing a calculation that includes friction or frictionless calculation. In addition, we wish to calculate the position and velocity over a sequence of times instead of just at a single time. Again, we import the exponential function from the math module. We'll define the function calc position velocity to create lists that contain the positions and velocities at a sequence of times. This function takes function objects which return the position and velocity as parameters. In addition, the parameters t-step and t-max have the default values 0.1 and 10 respectively. The first calculation is at time 0. An empty list is assigned to both position and velocity. A while loop loops until the time is greater than or equal to t-max. Each iteration of the loop, the function objects x and v are evaluated with time passed as the argument, and the results are appended to the position list and velocity list respectively. Time is incremented by time spent. After the while loop terminates, the position and velocity lists are returned. In the main function, values are assigned to variables that represent the initial velocity, the friction coefficient, and the mass. The user is prompted to choose a calculation that incorporates friction or one that does not. An if else statement is used to assign to x and v the lambda expressions that incorporate friction or the lambda expressions that do not. The user is prompted to enter the maximum time. The calc position velocity function is called with two function objects and tmax passed as the arguments. The position and velocity lists are assigned to position and velocity respectively. Finally, both lists are printed out. Let's run the code. First with friction equal to yes, and a maximum time 5. Now we'll run it again, this time with no friction and the same maximum time. Although statements and returns are not allowed in lambda expressions, you may incorporate a conditional in a lambda expression, thereby making the code even more compact. So notice the x and the v assignment statements inside of the main function. Suppose we had not used lambda expressions. How might you code this example? One of the different ways you could code this would be to define two calc position velocity functions, one that does not incorporate friction and one that does. Instead of calling functions that return the positions of velocities, those expressions could be directly coded into the two calc position functions. Notice that the first function that doesn't have friction takes v0, t-step, and t-max as parameters. The second function that incorporates friction takes v0, b, m, t-step, and t-max as parameters. Depending on the user's choice, the appropriate calculate position velocity function would then be called. While this program is syntactically correct, lambda expressions make for neater and more flexible code. To learn more about learning IoT with Python and Raspberry Pi, go to www.learningiot.net.